Boys and girls, look up here. I know this is going to be kind of hard for you to see, but it's exactly what is on your paper. So I am making a video of this just because I'm being prepared in case someone were to get quarantined. But anyway, this is just kind of what we did at the very beginning, and it's super hard to tell. But if this doesn't have an exponent by it, like this 10 doesn't have an exponent, what would its exponent be? It would be 1, you're right. So you can put that 1 there. You're never going to see them writing an exponent of 1. It's just not going to happen. It's invisible. Usually they just don't put it there. So I'm putting it there so you know, because if you think that there's a 0 there, that's completely different than you think that if there's a 1 there. 10 to the first power is 10, so it's like saying 1x. X and 1x mean the same thing. They typically just remove the 1 because you still have just an x. But anyway, we're just trying to write this in the other form. So you would write the big number first, which is 10. The exponent that's attached to the 10 goes on the top of your fraction, and then the root goes on the bottom, which it would be a cubed root, so that would be a 3. The second one is even smaller. It's hard for you to see up here, but the big number, the constant, is 3. The exponent that's attached to that is a 2, and I think that's a 5, right? Yeah. Okay. Okay, then on number 2, it's the opposite. They give it to you as a fraction. They want you to write it like we did like they gave you the first 2. So the A is what's going to go right under your radical sign. The top number is the exponent. I think that's a 2. Yes, that's a 2. And the bottom number is a root. So that would go right here in the little check mark part. Same thing with B. They give you the fraction. They just want you to rewrite it. So 3 would go under the radical. That is a 1. So you could see it like this and a 2, but this is the way that they're going to write this is just the square root of 3. If it's a square root with a root of 2, they're not going to write that, and they're also not going to give you that little 1. So these two things mean the exact same thing. Okay, number 3, it says solve this equation. We have 4 raised to the 3rd power, and then they also raised it to the x plus 1 power. And then the other side is 4 raised to the x plus 7. So since they both have a base of 4, you can go ahead and get rid of that. This would be 3 times x to the 1st power. And then this one, there's nothing to even do. It's just x plus 7. So now it's just a 2-step, not a 2, it's more than that. It's an equation that you can solve. If you want to draw your line down at your equal sign, I know that's how you guys learned in 7th grade. Some of you maybe, I don't know. This needs to be distributed, 3 does. So you're going to take 3 times x. And you're going to take 3 times 1. On the other side, there's nothing we had to do to simplify that, so we'll just leave it. This is something like this right here. This is something you may see on the 8th grade map test at the end of the year. That is solving an equation with a variable on both sides of the equal sign. 8th graders are expected to know how to do that. So there's a bunch of ways you could solve this. I always figure out the smaller value with x. There's one that has a 3, and then there's one that has like an invisible 1. I'm going to move this one. Only reason I do that is because I don't want to work with negatives all the time if I don't have to. If you like negatives, you could have moved the other one and you'd get the exact same answer. The opposite of positive 3 is negative 3. So it's 2x equals 4. So what does x equal? 2. X equals 2. Okay, we're going to go actually to number 4 right now. I know there's another one. I just haven't gotten to the other page yet. So it gives you on number 4, it gives you an equation, an exponential equation. It says identify the key functions of this function, f of x equals 10 raised to the x power, and its graph. You can go ahead and type these into your calculator if you want, or you could think about them without the calculator too. If I'm taking 10 to the negative second power, remember we don't like having negative exponents, so that would go to the bottom of my fraction. What is 10 to the second power? So this is like 1 over 100. I'm going to have a really hard time writing all of these fractions, but 1 over 100 is this x, or 10 raised to the negative second power. Then if you wanted to do 10 to the negative first power, it would be 1 over 10 to the first power. And we know 10 to the first power is just 10. So for 1, or negative 1, sorry, it would be 1/10. Anything to the 0 power is what? Nope. 1. 10 to the first power is what? And 10 squared. There we go. So now it's going to ask us some different questions about domain, range, and an asymptote. So anyway, domain is always your x values. So what kind of x values are you allowed to have? Well, what kind of numbers can you put in for this exponent? Does it matter? All real numbers. So if you want to write all real numbers, there's a little way you can write it that's faster. It's an R with 2 lines. That means all real numbers. That just means it does not matter what number you put in for x. It could be positive, it could be negative, it could be a decimal, it could be a fraction. All of the numbers will work. The range now, so we're looking at just our y values. What do you notice about our y values? They're all positive and greater than what number? 0. So our range is y. All of our y's, no matter what number we put, is going to be greater than 0. We kind of did one like this not too long ago. Even if I went down and did 10 to the negative third power, it's going to be 1 over 10 to the third. You're just getting smaller and smaller fractions, but you're never going to hit 0. That's what an asymptote means. It's never going to touch 0. So the asymptote is y equals 0. That is the line on that's like your x-axis right here on a coordinate plane. Y-intercept. When x is 0, what is y? That's right on your graph. When x is 0, what was y? So we would just write that ordered pair down. And those are the answers for that one. Number 6 is very similar. It's just a different equation. I wonder if yeah, here we go. Let's go over back to B first. So this is 3B. No, we already did this one. We did this one. We need to do this one down here. This one. Okay, so they both, actually, no, the first one on the left side has a base of 5, but the right side has a base of 25. So before we can do anything, we both have to have a base of 5. So I'm going to leave this one the same. But I know that 25 can be broken into 5 times 5, which is the same thing as 5 squared. So instead of writing the 25 like they have it, I'm going to actually change that to 5 squared. And I'm going to put that in parentheses, and then it's still raised to the exact same power as it was before. The only thing I changed, those are like, you can substitute those things in because 5 squared and 25 mean the exact same thing. So on the left side, I'm just going to write down my exponent. It's 10. On my right side, though, I have to multiply both of my exponents together. So I've got a 2, and I need to multiply it by 2x plus 3. This is now just an equation. Your left side still stays 10, and then you distribute your 2. So 2 times 2x is 4x, and 2 times 3 is 6. I'm going to give you a minute just to solve the rest of that equation. And find x. What'd you get? 1. Subtract 6, you'd get 4 equals 4x. Divide by 4, you'd get x equals 1. Okay, now we're going back to number 5. Okay, so your equation is 6 to the x power. And you can type these like into your calculator if you want. Sometimes it's easier for me to just look at them without a calculator. If I went 6 to the negative second power, that turns into 1 over 6 to the second power. I know that 6 to the second power is what? Yeah, so this is 1 over 36. Then if I did 6 to the negative first power, it would be 1 over 6 to the first power, which is just 1/6. Anything to the 0 power is 1. 6 to the first power, 6 to the second power. Okay, so now they want you to use this graph and graph these points. You've got tiny little fractions there. You just have to figure out as close as you can. Your graph is not very big, so you do the best you can with where those are. It also appears that our graph is going up by 3s. So if I'm going over to -2 and I'm trying to graph 136, it's basically going to be on 0 with our graph the way it is. So I'm going to put it just right above that line. Same thing with -1 and 1/6. I'm just going to put it right on that line. Now I can actually start graphing a little bit. 0, 1. I'm going to move it up just a little bit, like 1/3 of the way. 1/6 would be here. And 2/36 appears that it's not going to fit on the graph. So it would be somewhere all the way up here, though. Okay. Number 6, these numbers up here are super tiny, but what we want to do is it says write an exponential function. So remember your exponential function equation. This is just a normal exponential function. You take a times b to the x power. So we have to know our initial value. So when it's at 0, what's our first number? Yeah, when x is 0, what's our y? 6. That's our initial value. And to find b, we have to figure out, we're just looking at our y's, and I know this is so tiny, but it goes from 6 to 12. How much do you multiply by? 12 to 24, you're multiplying by 2. So you can tell what your b is, so it would be 2 and then raised to the x power. Okay, number 7. Ines saves $5. She doubles the amount she saves each week. Does this represent an exponential function, and explain? So what do you think? You think yes, it's exponential? How would you know that? Yeah, the word doubles tells you what you need to know. And then it asks us some questions about her. It says, how much will she save in 2 weeks, 3 weeks, 10 weeks? Show how you found each amount. This is really up to you. There's a lot of ways you could do this. You could use the formulas, but if it were me, I'm going to make a table. That's just who I am as a person. I like 1 week she has $5. How much would she have in 2 weeks if her money doubles each week? How much would she have in 3 weeks if it doubles? Okay, so we did 2 weeks, 3 weeks. Now we need 10 weeks. So we need to come up with an equation for 10 weeks, unless you just want to keep doing that until you get to 10, which is a fine way to do it. Just takes a while. So we're going to make an exponential function for this equation. She starts with $5. That's your initial amount, and we know that it doubles every week, so that's where the 2 comes in. If I'm doubling my age, I'm taking my age times 2, and then raised to the x power. So if you want to know after 10 weeks, you would plug this in. where X was. Yep, $5,120. Can you imagine? This is not a realistic scenario because apparently in week 10, she would have to double how much she's saving. If she must be bringing in a lot of money to be saving $5,120, but she makes more money than I do. That's not hard to do. Okay, now we're going to go to number 9A. Tia invests $2,500 in an interest rate of 4% compounded quarterly. How much of the investment is how much is the investment worth at the end of 5 years? So this is compound interest, and it tells you that. Basically, it tells you that you compound quarterly. So if it ever says compound, you know that you're using the compound interest formula, and I'm just going to write it down for you. A equals your principal. 1 plus, this would be your interest rate divided by the number of times you're compounding, and then this is N times T. This is just directly from your notes. This is the compound interest equation. I know I'm using compound interest because it literally says you compound it quarterly. So anytime it tells you how much you're compounding, this is the equation you would use. Most likely on any situation, they would give you all these equations. You would just have to know which one was which. So anyway, principal amount is $2,500. So that's your P. 1 plus the interest rate, it has to be written as a fraction, or not a fraction, a decimal. So 4% would be 0.04. And then if it's compounded quarterly, what would that number be? 4. There's 4 quarters, so. And then you take 4 times the number of years that she's wanting to do this, which is 5 years. I would type it into my calculator just like it says on my board, like exactly like that. Even the parentheses and everything. That's not correct. Okay, so let's make sure we're typing it in our calculator right, because I got like. Okay, so I'm gonna just type it in, and I'm gonna show you how I typed it in. I typed in $2,500. That's our principal amount plus, and then I'll do a parentheses 1 plus 0.04 divided by 4. I just typed it in just like that because order of operations is going to catch that. You do division before you do addition, so that's fine. It'll catch that. And then I'm going to raise it. What is 4 times 5? 20th power. $3,050. Do you guys know what you typed in wrong, or? Oh, okay. Yeah, just simplify that. Okay, so I'll write it up on the board so you can see. There it is. $3,050.48. Okay, now we have another compound interest problem, and here's our equation that we're using up here. Tio invests $3,000, so we know that our P stands for 3,000, our principal amount. But this time he has a different interest rate. So he has an interest rate of 2.5%. So if you're writing that as a decimal, it would be 0.025. But this time it says it's compounded weekly, so you have to know how many weeks are in a year. So that's the bottom number of my fraction, 52. 52 weeks in a year. And he wants to know after 5 years, so you would end up taking 52 times 5. And I would type it in just like that, but instead of taking 52 times 5, that's the same thing as 260. So I'm going to raise it to the 260th power. So I'm going to go ahead and type this in. You guys do the same. We'll see if we get the same thing. That is correct. Okay, so Tio ends up with $3,399.34. So the next question on C, I'm going to move over. Does everybody have that? 0.025. It's a really small percent. So if you did 2%, it would be 0.02. Since it's 2.5, you have to add that 5 in as well. So on C, it just says, who has more money? Why do you think there's a difference? What would happen if they left their money in for a longer term? So here's C. Who has more money at the end? Tio or Tia? Tio has more money. Why do you think that is? Nope, they both put $5,000 in at the beginning. It has to do with how much it's being compounded. Tio's is being compounded 52 times a year. That means 52 times they recalculate the money and he makes money on that. So Tio makes more, and it's because it's compounded more often. So Tio's is only being recalculated 4 times a year, but Tio's is being calculated 52 times every year. And oh yeah, he did start. Whoever said that, I apologize. He did start with $500 more though. Sorry, Grady, I didn't even look at it. But it does, if they started with the same amount, he would most likely be making more because he's being compounded more. His is being compounded more. Let's go to 8 now. The population of a town is 14,000 and it grows. There's your keyword there. It's an exponential growth function at a rate of 4% per year. What will the population be in 6 years? The hardest part about these is figuring out what equation you're going to use, because like in the last one, we had to use the compound interest equation. In this one, it's an exponential growth. So that equation is it's a plus 1, or what is it? A times. You take your initial amount, which is A, $14,000. You're going to take your rate, but you have to add 1 to your rate. So I'm going to take 1 plus 4%, which is going to be 1.04. You have to add 1 to your rate because you have 100% of the people who are in the town and 4% of new people. And then you raise it to the amount of years. So since this is an exponential growth, I had to add to my rate. Add 1 to it. This is going to tell us how many people would live in this town after 6 years. 17,000 something. Yeah. We're going to just leave it 714 because we're not going to have 0.47 of a person living in our town. That's just not going to happen, and we're not going to talk about that. What will the population be in 20 years? Do you think this is realistic? Why or why not? We're going to use the exact same equation that we did. Instead of 6, though, we're going to use a 20. So we're going to see, according to this growth function, how many people would live in this town after 20 years. And then they asked, is this realistic? 30,675 people. So we started in this town with 14,000 people, and after 20 years, we have 30,675 people. This is more of an opinion, but do you think that's realistic? Why or why not? Like, if you think no, tell me a reason. Okay, so if you think that it is realistic, someone give me a reason why. I think it's realistic. If a big company moved in, or like say, I'm going to take Neosho for an example. We all know where Neosho is, correct? Okay, they have a bunch of, like, they have the Tyson plant, and now they have like 2 or 3 big plants coming into their town. So it's just growing and growing and growing. But what do you have to make sure to do if your town is growing? You have to make sure you have housing for people and available jobs. So if you have a big company come in, like say another 3M came to our town, would we have more people living here? Yeah, because jobs would come into the town, okay? So it really just depends on what's happening. That's 20 years, you guys. 20 years, a lot can happen, right? Like a lot of jobs can, we're not going to go there, but okay. We're going to move on to number 10. I would say, to me, I would say it would be realistic if there were enough jobs available. There are 4,200 bacteria in a lab. The population decreases by 8% per day. Write a formula to show how many bacteria will be left on the 12th day. This is a decay function. So you start with your initial amount, $4,200, not dollars, bacteria. But in this case, it's a decay function. We're going to take 100% minus 8%. Due to the fact that this is a decay, you subtract your percentages. So what's 100% minus 8%? And now I need to write that as the decimal. How do I write 92% as a decimal? And then they want to know on the 12th day, so we would raise it to the 12th power. Obviously, this is a decay function, so if you're getting something bigger than what you started with, you did something wrong. So 4,200 times 0.92 raised to the 12th power. And that would be how many bacteria are left. Yep. All right, we're going to get through the rest of these really quickly. Now we're talking about sequences. So we're talking about like recursive sequences, geometric sequences, all of that, explicit sequences. So on number 11, it says the sequence 10, 5, or 15, 22.5, 33.75. Is that a geometric sequence? Easy way to figure out if you have a geometric sequence, take 33.75 divided by 22.5. See what you get. 33.75 divided by 22.5. Okay, now take 22.5 divided by 15. And 15 divided by 10. Okay, so we know that, yes, this is geometric because we got a common ratio. The common ratio is 1.5. When we divide, we got the same number every single time. That represents a common ratio. If I got a different number every time, that would not be the case. Down below that, what is the explicit and recursive formula for this sequence? We start with 540, then we go to 180, 60, 20. Explicit formula is kind of like the exponential function, but the first thing we have to do is figure out what our common ratio is. So I would take 20 divided by 60 and see what you get. 1/3. We have to take our first number times 1/3 to get to the second number, and our second number times 1/3 to get to our third number. So our common ratio is 1/3. So we're going to write that down. We also have to know the initial amount we started with. How much did we start with? What's the first number in our list? 540. Okay, so our explicit formula, we're starting with A sub n. That just means if I wanted to know the 100th number in the sequence, I would change the n to a 100, right, Shannon? Okay. 540 goes first, times our common ratio, which we figured out was 1/3. And then it would be to the n minus 1 power. Once again, this is just an equation you'd have to, it wouldn't just make you memorize all of these. They'd give you like a form with all the equations on it, and you would have to know how to use them. There's a lot of equations to remember. The recursive formula, the only thing you have to know is your common ratio. So A sub n equals the common ratio, which is 1/3, times the previous term, which they write like that. So say then the term is 20. If I wanted to know the next term, I'd take 20 times 1/3. Now they want to know the fifth term. You could use, we know the fourth term, so the easiest thing would be to take 1/3 times 20. So the fifth term is what? Yeah. You could have used either equation and plugged in a 5 where n was, but since we had the fourth number in our list, I think it's easier to just take it times 1/3 than to plug it all the way into that. We have a couple more questions to go over. I don't know, did we do? We'll just start on 14. The recursive formula for a geometric sequence is A sub n equals 1/5 times A to the n minus 1. With an initial value of 125, what is the explicit formula? Okay, the only thing we care about in this equation right here is it tells us our common ratio, which is what? 1/5. The only thing that a recursive formula tells you is your common ratio, and then right here it tells us the other important information, which is our first term, which is 125. So it would be A sub n. Our first term is 125. That's the number in our list. We're going to take it times the common ratio, which was 1/5 to the n minus 1 power. The last problem on number 14, actually we have a number 15, I guess. So the recursive formula is this. With an initial value, what is the explicit formula? This is the exact same thing we just did. The only reason a recursive formula is good for anything is it tells you the common ratio. Common ratio is 4. First term right here, it tells us is 12. So it's the exact same thing we just did. We start with A sub n. We write down our first term, which in this case is a 12. We're going to take it times our common ratio, in this case is a 4, and raise it to the n minus 1 power. And then I think we have one more problem. We're going to get through that, and then we'll be done. Are you guys good with that? Can I move on, or do you need a second? Did we do 13? Okay, so we need to do 13 and 15. I'm going to skip the 25th term. If you want to do that, you can. It's a big number, so the explicit formula for a geometric sequence, here it is. Now they want the recursive formula. The only thing we care about in this sequence is what the common ratio is, and that's the number in parentheses, which is 3. So your recursive formula would be A sub n. Remember, like I said, this number in parentheses is the number we care about. That's our common ratio. So we would take 3 times the term that comes right before it. They say A to the n minus 1. That just means that the number in the list that comes right before. 15, the population decline of African elephants can be modeled by an exponential function where f of x is the elephant population, x is the number of years since 1900. The elephant population was 12 million in 1900 and declined 3% each year. Write the function that relates the elephant population to the number of years since 1990. So, 1900, sorry, I don't know why I said that. Okay, so we just need to write, it's a decay function. So, what is our initial value? How many did we start with? Ugh, that's such a large number to write down. 12 million is our initial value. If this is a decay function, we're going to take 100% minus 3%, which is how much? It would be 97%, so we take it times 0.97, and then raised to the x power. That's the function that we're using, and then it says the population decline continues. Estimate the population in 2020. Hint, think about how many years have passed between 1900 and 2020. So x would be 120. 12 million times 0.97 raised to the 120th power. What'd you say, Gannon? So 12 million times 0.97. Yeah. We're going to keep that a whole number because we're probably not going to have parts of an elephant. So that's how many elephants after 120 years, and that's really sad because considering you started with 12 million and now you only have 310,000, that makes me sad for the elephants. All right, you guys, you can put that away.